Hey guys, so today we're going to do Unit 4, Lesson 1, and we are describing and graphing situations. So we're going to look at some functions around us and try to describe them. Well, I am, and you're going to listen. So the form up today is about a bagel shop, and a customer at a bagel shop is trying to buy 13 bagels. The shopkeeper says, all right, 13 bagels, that's going to be $16.25. There's a couple of people there, Jada, Priya, and Han, that are there, and they all think that this is a mistake. Jada says, shouldn't the total be $13.25? Priya thinks, oh, it should only be $13. And Han's like, y'all are all wrong. It should be $11.25. So explain how the shopkeeper, Jada, Priya, and Han could all be correct. All right, now that you've put your thoughts in there, I'm going to go through it for you. So if you're looking at the shopkeeper, how could the shopkeeper get $16.25? He has this list of prices here for you. And he says, all right, one bagel costs $1.25. So 13 bagels at $1.25 is going to cost $16.25. All right, that seems fair. What Jada did, Jada says, oh, well, I can get a 6-pack of bagels for $6. So I need 13 bagels. So I'll take 2 6-packs plus 1 bagel. All right, so that gives me 13 bagels, and that price is going to be $6 plus $6 plus $1.25, and that gives you $13.25. Okay, so that's how she's right. And then you have Priya. She thinks it should only be $13. Well, Priya says, oh, looky here. 9 bagels is only $8. So if I buy a 9-pack and then I add 4 more bagels to that, I'm going to only pay $13 because a 9-pack is $8. And then I need 4 more bagels that cost $1.25. So I'm going to pay $13. And then Han over here, he says, y'all are all crazy. A 12-pack of bagels only costs $10. So I can buy one 12-pack plus 1 more bagel. That gives me 13. And so $10 plus $1.25 for the additional bagel. I'm only going to pay $11.25. So they are all correct, but it's how you order it. So this is a bagel example where you see the same thing costing a different amount. Well, let's look at this in a table format for us. On this next slide, and you have this information that you can see. So here, the first column is the number of bagels. So how does this relate to what a function is? So your pretest you took represents it had questions about functions and different things on it. So this whole first column are your x values or your input. So this is our x value. And your x value is also known as the input. Okay. And what you get out of a function are all of these prices over here. Okay, so all of these prices are your y value. Can't really read that. And it's also known as the output. Okay, so you have an input or an x value, and an output is your y value. So for our input, if I'm wanting to buy a specific number of bagels, like 1 bagel, I know I'm going to pay $1.25. 2 bagels, $2.50. 3 bagels, $3.75. But when I get down here to 6 bagels, I now have 2 prices. So if I buy 6 bagels at $1.25 each, I'm going to pay $7.50. But if I buy the 6-pack of bagels and do it Jada's way, I'm only going to pay $6. And then when we get down here to 9 bagels, you can pay $11.25, $9.75, or $8. If you buy a 9-pack, they're even cheaper at $8. And then 12 bagels, you have another decrease because a 12-pack only costs $10. So each of these sets here create an extra output. So this is not a function. So we would say that this is not a function, okay? So over here, our output is the price of a bagel. So the price of bagels is not a function of the number of bagels you buy. And that kind of seems crazy to us. Okay, because we want to think about buying something as a set price. And this is something that we kind of see in the real world. One example that comes to mind, if you go to McDonald's, you can buy chicken nuggets, right? So a 4-pack of chicken nuggets is on the dollar menu. So you can buy a 4-pack for $1. Well, if I get 3 4-packs, I have 12 chicken nuggets. I'm only paying $3. But if you buy a 10-pack of chicken nuggets, they're almost $6. So it's cheaper to buy 3 4-packs and get 2 extra chicken nuggets than it is to buy a 10-pack of chicken nuggets. So this is things that happen in the real world, things that you see that you don't really think about. So this is not a function because the number of bagels as your input can give you multiple outputs. But we can make it a function if we look at the best price. So if we want to compare the number of bagels to the best price of bagels, then we're only going to have one output for each of these. And so we would find the cheapest price possible, and that would be the best one for us. Okay. And so now for every set input, so all of my inputs over here, I have exactly one output. So there's only one output. So for something to be a function, each input has exactly one output. And we write our sentence as y is a function of x. Okay, and we're talking about our x and our y like an xy table. So over here, we would say the best price is a function of the number of bagels. Okay, so another way to think of a function is looking at a Coke machine. If you go up and you push a button on a Coke machine, if I want a Mountain Dew, I'm going to push the button that says Mountain Dew. If it gives me a Mountain Dew, that function works. If I push it again and it gives me another Mountain Dew, then it is a function. But if I go up to that machine a third time and I push the button for Mountain Dew and it gives me a Dr. Pepper, then that is a broken Coke machine. It doesn't work anymore. It's a broken function. So it does not meet the requirements to have one output for each input. All right, let's look at this another way. Another way is to look at a vertical line test. So if a graph passes a vertical line test, that means that it only touches your graph one time. Okay, so if I draw a vertical line on this graph, it touches 2 points. 2 points on that line. So it is not a function. It fails the vertical line test. Over here, for the best price in bagels, if I draw a vertical line, it's only going to touch it one time. So it is a function. Some more examples of graphs that would not be a function. So if you have a graph and it goes like a zigzag like this, and you draw a vertical line down it, you can see that it's going to pass through that 3 times. So it touches that 3 times, so it is not a function. If it just makes a U, it is not going to be a function. If you have an exponential function, it goes up. It's only going to pass it 1 time, so it is a function. A quadratic function will only touch the line 1 time, so it would be a function. And a vertical line does not pass the vertical line test, so it will not be a function. All right, so let's look at another problem. We've got a dog. He's being put on a leash tied to a post. So the dog's leash is 5 feet long, so that's as far as the dog can move away from the post. And day 1, the dog walked around the entire time while waiting for its owner. Day 2, the dog walked around for the first minute and then laid down until the owner returned. Day 3, the dog tried to follow his owner to the store but was stopped by the leash. So each day, the dog was 1.5 feet away from the post when the owner left. So what time is it going to be when the owner left? All right, so when the owner leaves, it's 0 because he hasn't left yet. That's when he's leaving. So he's going to be 1.5 feet away from the post at 0 seconds. And then at 60 seconds, the dog is 4 feet away from the post. So you would put a point at 60 seconds and 4 feet. So we know that that's where the dog is. So on day 1, I'll make it blue. So the dog walked around the entire time while waiting for his owner. So we know that at the red point is where the dog was at those specific moments in time, but we don't know anywhere else the dog went. So as long, can the dog be at 2 places, like 2 distances away from the post at any given time? Of course not. He can't be 2 places at once. So the line's not going to be on 2 different points, but it can move in any direction. So it could look something like that if the dog walked around the entire time. He could have went up here and then down and then around. We don't really know where the dog went, but he could have done something like that, either of those. Day 2, the dog walked around for the first minute and then he laid down. So if he's walking around for the first minute, he's moving and then he lays down. So if he's not going to change any distance after he lays down, he's going to remain 4 feet away from the post there. And then we have day 3. Day 3, the dog tried to follow his owner to the store, but was stopped by the leash. So if he was stopped by the leash, we know that he at least went 5 feet away. So maybe he followed the owner and then hit the leash, and then he walked around in a circle until he ran out of leash. So walking around in a circle, he's going to slowly lose distance between him and the post, and then he would lay down. Okay, so it could look any of those things. Yours might have went up more quickly and then went down. It doesn't really matter because we don't have any specific times other than 0 and 1.5 feet and 60 seconds and 4 feet. Okay. Another thing I want to look at. So in this specific situation, we would say that the distance from the post is a function of time. But can we switch those? So if I rotated that graph and I said the time in seconds is a function of the distance from the post, that would create a false statement because for distances, so if you're looking at the green line, at 4 feet, or let's do 3 feet. So at 3 feet, if that was now my x-axis, so I've just turned it, this line is at 3 feet at like 18 seconds and about 90 seconds. So that would give me 2 outputs. So it would no longer be a function. So usually time cannot be a function of something else because it can occur and it can happen multiple times that someone can be 4 feet away from a post. But time is linear and it's not going to occur more than once. All right, so we're going to look at two pairs of situations. So the first one is time in seconds since the dog owner left and total number of times that the dog has barked. So we looked about distance from a post, but what about number of barks? And you have to pay attention that it says and the total number of barks. So those are accumulating. So in that function, so looking at number one, which variable is independent? So our two variables are time and number of barks. So the time in seconds since the owner left is your independent variable because it's not going to be affected by the other one. The total number of barks will be your dependent because the dog can bark at any given time, but it's going to change over time. Time doesn't change. It's not affected by anything else. So it is almost always your independent variable. So that means that the total number of times the dog has barked is a function of time since the owner left. So that's how we write our sentence. So always think of it as your y variable is a function of your x, or your dependent variable is a function of your independent variable, is another way that you can think of it after you figure out what your independent and dependent variables are. Okay, and here's a graph of what that might look like. So we have time is our independent variable down here on the x-axis, and your y-axis is your dependent variable. Okay. So as time grows and goes on, the total number of barks increases over time. Okay. Let's look at another one. So what about the time in seconds since the owner left and the total distance in feet that the dog has walked while waiting? Well, the dog can continue going back and forth, zigzagging within a 5-foot radius. So he can't, if we were just mapping his distance, he couldn't go more than 5 feet away from that post. But now we're talking about total distance. And so as long as he's walking back and forth, he's still adding distance to his total. So if we're looking at that function, the independent variable would still be time. Time is almost always your independent variable. Okay? And then your dependent variable is going to be the total distance that the dog has walked. So if we're completing a sentence, that is your dependent variable is a function of your independent variable. We would say the total distance that the dog has walked is a function of the time in seconds since the owner left. So we know that the dog is going to go further the more time goes on, or the less time is the less distance that the dog went. And so if you look at this graph, you can see your independent variable on your x-axis and your dependent variable on your y-axis. And so you can see that it's steadily increasing. It's not at a constant rate because, the dog's not going to walk in a constant speed the whole time that its owner's away. So you got to consider all the factors that go into that. It's not going to be constant. It's going to kind of be sporadic. So hopefully now you can understand the relationship between two quantities being a function. You understand that one input can only have one output that is specific for it to be a function. You can use words to describe something being a function of something else. So your dependent is a function of your independent, or your y is a function of your x, and kind of make sense of some graphs and functions and explain what they tell us about in a situation.